Okay. Just so you know, I've started recording. All right, cool. Okay, all right, and then I'll have this posted and shared. Okay, so plot for today. So last time we talked about um, types of solution sets and got into homogeneous systems, and today we'll follow our nose on the homogeneous systems and talk non-singular matrices, and time permitting, we'll get into some vector operations. Okay. All right, so let's recall that given a matrix, you can always create a homogeneous system by just taking the entries of the matrix and making those the coefficients. Okay. Now, right, matrices exist independent of systems, right? A matrix is just a rectangular array of numbers, or broadly math objects. You can put things other than numbers in. Cat showing up, one of the three cats. You can put something other than numbers in your matrix. You can put functions. You can put matrices inside matrices. You can go nuts. For us, we're just going to stick with numbers for the most part. Right, these exist without systems, but as we know, every system yields a matrix that you can then work with. But you can go backwards. Given a matrix, we can then form a system, and in particular, if you make the right-hand side all equal zeros, like this homogeneous system, and the set of solutions of these is called the null space of the matrix, denoted by n of a. As we noted, that's my notation. Our textbook will use a fancier n. There it is. Ooh, but we'll stick with just plain old n. I don't feel like typing out the commands to make the fancy fancy n. All right, but my favorite matrix here: 1, 2, 3, 4, 5, 6, 7, 8, 9. This matrix, if you create the associated homogeneous system, then it's pretty easy to find the null space by just literally solving the system. All right, cool. And there we see we've solved it. And note that the z variable is free because in the reduced row echelon form, the first two columns are pivot columns. The third column fails to be pivot, so that variable is free, and thus will show up. Okay. All right. Now that we're back up to speed, let's talk about some facts about the null space. What are some things that are always true? And perhaps the most important thing about the null space is that it's non-empty. That's not the most important thing. There's going to be quite a few important things we'll uncover as the semester goes on, but this is a big one right off the bat, that there are always things in the null space of your matrix. And in particular, there is a specific element that is always in there. And we'll give this a notation. The vector consisting of all zeros, which we'll use a bold 0 to indicate this, usually referred to as the zero vector. Or is always an element of the null space, right? And going back to this homogeneous system up here, that just corresponds to replacing all the x's with zeros. And then, yeah, you get 0 equals 0, which is true. Right. So this vector is quite nice, and as we talk about vector operations going forward, we're going to find out that this vector is very nice and has a lot of is sort of the pivot point for a lot of things that you do with vectors. All right. Okay, so we always know that you've got at least this thing hanging out in the null space. And a big question to ask is, when are there other elements? Right, and that would correspond to your homogeneous system having non-trivial solutions, which we noted is a possibility, right? In fact, we see it right here with this matrix. This null space has non-zero things in it. All right, now something that we know about homogeneous systems is that if there are more unknowns than there are equations, well, then there are never going to be enough pivot columns to fix every variable. So when the number of equations m is strictly less than n, then there have to be other things, because homogeneous system we then know has non-trivial answers. So that's kind of a quick sort of just immediate fact. If your homogeneous system has non-trivial answers, right? Well, that happens when you don't have enough equations. Right? So if your matrix does not have enough rows, so if it has more columns than rows, there are always things in the null space other than the zero vector. Now, this inequality then leads us to ask, all right, well, what happens if you are in the situation where m is not strictly less than n. What can happen then? Right, so when m is strictly less than n, we know that the system has non-trivial answers, guaranteed every time, no matter what. What happens when m is at least n, if not more? Note that would correspond to the number of equations either equaling the number of variables or exceeding the number of variables. All right, well, let's go ahead and look at three matrices and investigate their behavior and compute their null spaces. Give us a little bit of an idea of what might happen when m does exceed n. And here we have three examples. In case one, there are 3 rows, 2 columns, so the number of rows outdoing the number of columns. In B, we have 4 rows and 3 columns, so again, the number of rows exceeding the number of columns. And in matrix C, we have an equal number of rows and columns. And note that it's almost my favorite matrix, but I've changed ever so slightly one of the entries. And as we'll see, this has fundamentally different behavior. All right, so when it comes to computing null spaces, you can, of course, convert these over to systems, but then you're right, you're just going to make augmented matrices and then get the ref, and the last column is all zeros, so the ref really doesn't give a shit about that. Maybe I shouldn't have sworn in the recorded video, whatever. I'm sure those were things they've said. Anyway, so we don't need to go for that whole process. We don't need to create the system of equations, augment the matrix. We can just directly compute the refs of these three. And these refs are pretty easy, almost to eyeball, in fact, right? Because matrix 1 here, matrix A here, this 1 clearly will delete the 2 and the 1 below it. The 0 will not affect the other entries. And then the 6 can be scaled to a 1, which can then delete that 1 down there. So the ref of our first matrix is pretty easy to sort of see. Same thing for B. We already have a beautiful pivot column going on in column 1. And in column 2, we can kind of isolate this element and then delete everything above and below it and create this ref right here. Right, note that is in reduced echelon form. And here we have 2 pivot columns, and the third one fails to be pivot. All right, but it's definitely in ref. 0's at the bottom, staircase pattern, leading coefficients of 1. Leading coefficients are the only non-zero things in our columns. And then finally for matrix C, you can compute the ref of this if you want. I'm not going to write it out, but you will indeed get this beautiful matrix with 1s on the diagonals and 0s elsewhere. I wonder if this is a special matrix that has a special name and a special symbol. Ooh. All right. Anyway, so if the ref's computed, you can actually directly compute their null spaces pretty much immediately. So let's go ahead and do that. All right. So matrix A and matrix C are pretty easy to compute their null spaces because, well, in matrix A, every column is a pivot column. And as we know, if you're dealing with a homogeneous system, if every column is a pivot column, then all of the variables have to equal 0, because that's what the right-hand side is. And there you go. Every column is a pivot column, so that means you got to have a unique answer. And since there's only one answer already that we have access to, it's got to be the only one. Likewise, for this 3x3, we have 3 pivot columns. That means we have to have a unique solution. We already know there is one solution, so it must be the only one on the set. Okay, but what about matrix B? Let's go ahead and compute its null space. Right. Note that column 1 and column 2 are pivot, which means column 3 is not pivot, which means the variable associated with column 3, which is the variable z, is free to be whatever it wants to be. All right. Now, row 1 here, I've got 1, 0, 1. That would correspond to x plus z is equal to 0. So if I were to solve for x, that would give me a negative z. So my first entry in my solution vector, which note is going to be a list of 3 things because there are 3 variables. The first variable x from this first row we know has to equal negative z. Now for my second row, I can tell you that my second variable y must in fact equal 0. right? It appears by itself in that row. So in terms of the equations, it would be y by itself. It's a homogeneous system, so the right-hand sides are equal to 0. And finally, z is the free variable, so z is just going to chill out down in the bottom there. There we go. There you go. Directly computed the null space of a matrix, and note I did not convert it over to a system. Right? I just directly computed the ref, and then from there just figured out what it had to look like. And this always works. You can always do this. Okay, and note this null space is something interesting going on with it. Here, the free variable appeared in all three coordinates of our solution vector. However, here, it does not. There's one variable that's just always equal to 0. And that can happen. Good stuff. Interesting thing to note. All right, cool. There we go. So computed some null spaces, and as you will do on your homework there, problem number 5 is asking you to compute null space. Do a similar sort of technique. All right, so here we are in the situation where the number of rows is at least the number of columns, if not more. And we see that, well, sometimes you only have the trivial solution of the 0 vector, but other times you might arrive at other solutions. So when m is strictly less than n, we always know there are non-zero solutions or non-trivial answers to that homogeneous system. But when m gets bigger than n, well, sometimes it is and sometimes it isn't. So naturally, I want to focus in on, all right, well, when does the null space only have the 0 vector in it? So we probably want to give that a name. And furthermore, as our A matrix here illustrates, that big fat row of zeros at the bottom really doesn't seem like I need that there or worry about it. Right, so let's go ahead and then focus in on the case where n is actually equal to m, when the number of rows and the number of columns are the same. Because, right, even here when I had a trivial null space, in this row of zeros, right, who cares, right? What really mattered was going on up here. All right, so we will go ahead and focus in on the case of n is equal to m now. And these are square matrices, right? And that's literally in the name, right? It's the number of rows and the number of columns are the same. So, right, it's not a true rectangle. Right? It is a rectangle, but right, it's not uneven. There's an equal, the sides are equal, so it's a square. Okay, and as noted, what we care about is the situation when the null space is in fact trivial. Right. And so we'll give that a name, and time for my favorite rant. So a matrix that is square and has a trivial null space is called a non-singular matrix. And this one I'm not afraid to say on camera. This is the dumbest name for anything in mathematics, I think. Right, because think about it, like the defining property here is that there is a single element in your null space. Let's call that non-singular. Bro, that is infuriating. Now, there are like deep lore reasons why this is actually called non-singular. It's got to do with singularities and like there's a reason for it. But I've always hated it. I've always thought it was a terrible name. It's stupid. It's dumb. I don't like it. And it's one. There's a few math hills I'm willing to die on, but I think this is the big one. Non-singular is a terrible name for this. Later on, we're gonna find out that our matrix is in fact an invertible matrix. I think that's a much better and descriptive name. So, in my opinion, it's got some points to it. But there are people that call this non-singular, serious math people, even more serious than me. So, it's unfortunate state of affairs. But anyway, okay. So we have seen a couple of non-singular matrices. So this one right here, C, non-singular, beautiful. We've kind of encountered matrices that ref to this particular matrix right there. And hey, maybe that's an equivalent condition. So let's go ahead and note that being non-singular is equivalent to a couple of things. So note being non-singular means that the null space only has exactly one element in it, which would mean that the associated system of homogeneous equations has exactly one solution, and the only way that could ever happen is if every column is a pivot column, right? Homogeneous systems are always consistent, so they always have answers. And if every column is a pivot column, well, then there can only be one possible answer, right? And being non-singular forces that, and vice versa. If every column is a pivot column, there's exactly one answer, so your null space has to just be the zero vector, right? And note the set theoretic way, I don't think I pointed that out, of denoting this with a curly braces around the single element. Okay, and furthermore, if every column is a pivot column and you're nice and square, well, what we see right here ends up being kind of the only thing you could ever look like in your terms of your reduced echelon form. So indeed, every column being a pivot column can only happen if my matrix is row equivalent to a matrix with 1 on the diagonal and zeros elsewhere. And this is known as the identity matrix. Ooh, here it is. Beautiful ... dots all over the place. All right, and indeed, this is the matrix with 1 on the diagonal and 0 elsewhere. So note, if you are row equivalent to this, that has to be your ref, because note that matrix is in reduced echelon form, and note that this means that every column is a pivot column, which would then mean that your matrix is non-singular. So all three of these things mean the same thing. Being non-singular means your null space is trivial, means all your columns are pivot columns, means that you're row equivalent to the identity matrix. All right. That's the story. There you go. Cool. All right, so there we go. We got several ways now of looking at this. And as we go forward, this is going to be very powerful and very useful. And for now, I'll leave you with one more thing about the identity matrix. So we'll explore this stuff a little bit more further once we get some matrix operations. I've kind of already let it slip that non-singular are invertible matrices. We'll talk more about that later. But let's note some size notational things here. So the identity matrix, when you announce it, you'll always use a capital I, but sometimes you need to indicate, well, which identity matrix is it? Right, because there's obviously the 2x2 identity matrix, there's also the 3x3. And while they're going to have kind of the same function, they have different sizes, and size matters with matrices. So we need to sometimes announce which identity matrix we're working with. And the standard way of doing this is to put kind of just a footnote of, oh, this is the 2x2, or this is the 3x3. Right? I'll do I sub 70 if I want the 70x70 identity matrix. And it's worth noting that, yes, you can have a matrix that has exactly one element. You can have a 1x1. And just like the empty set, they kind of like fill in a little gap of like, yeah, you kind of need this because while it's kind of ridiculous and you don't, why would you ever consider this? Right. When you're talking about a system of equations, you don't have like one equation and one unknown. Like it's not, what the hell is that? But right, these sort of extremal cases we need to be mindful of and have notation for, so we can deal with them when they pop up. There you go. All right, cool. So, all right, like I said, we've now got this nomenclature. We have isolated the special type of matrix called non-singular, which is a square with a trivial null space. Every column is a pivot column and a row equivalent to the identity. We have all this beautiful stuff set up, and this is going to be great. Again, once we start talking matrix operations, because we'll have an identity that we can work with, hence the name. But before we can get to matrix operations, we're now going to address the next topic for today, vector operations. So we'll build our way up to matrices by first addressing the case of vectors. All right. So, in order to properly do this, let's introduce a notation for sets of vectors. So, in particular, we will use Rn and Cn to indicate the set of vectors consisting of real or complex number entries, where the end indicates how many elements are in my vector. Right, so for example, this thing right here would be an element of R3. There are three things. And this is just another example of a situation of kind of why I prefer my natural numbers to begin at 1, because when I'm dealing with vectors, right, the first one I think of would be R1. Again, that's a little ridiculous. It's a vector consisting of one element, right? But you need it. It needs to be there. R2 obviously is a bit more of a natural thing. Excuse me. But right, you're right. If we start with 0, then you've got a vector with no elements in it, and right, that's ridiculous. Okay, so as mentioned, we're primarily going to be hanging out with the real numbers, but every so often we gotta go call on our friend the complexes because there's a problem that the reals can't solve that the complexes can. All right. Now, to make things a little bit more concrete, kind of already mentioned it, but R2 is the set of vectors of length 2 with real numbers. So two real numbers. And note that you can kind of think about this as the usual Euclidean plane, where there's an x coordinate, there's a y coordinate. Right, and that sort of geometric intuition is going to help us out here and there. One who generally avoid geometric intuitions can be incredibly misleading, but every so often it doesn't lead us astray. Here is C3, so a list of three complex numbers. All right. And C3 is a nightmare. C2 is also a nightmare. The complex numbers are great. But once you get several complex variables, which is a branch of math, just nothing works anymore. There's no theorems. There's just nothing but counterexamples. It's hot garbage, man. All right. So these are our vectors, spaces that we're going to be hanging out with. Let's note some notational things before we move on. When I'm going to need to refer to elements from these sets, I'll write them in bold. So for example, like a bold X. Usually we'll use that for the reals. A bold Z, which is usually reserved for complexes, but we can also include a bold Y as well. And what we can refer to and entries of the vectors, we can refer to them as the vector with a subscript indicating which specific element in that list I am interested in. Okay, so for an example of this, so we're all good on kind of a notation. And let me spice this up. Let's throw in a minus sign. Let's throw in a 0. Let's get everything. That's a better vector. All right. So for example, if I give you the vector z and it's got entries 1, 0, -3, I, this belongs to C4, great name. And each entry can be listed out. So for example, Z1 sub Z sub 1 is in fact equal to 1. Z sub 2 is equal to 0. Z sub 3 is -3. And Z sub 4 is I. Yeah. All right. So when I'm talking about vectors, right, we're usually hanging out in Rn or Cn, and we'll write the elements in bold typically, and then we can refer to specific entries by using our good friend the natural numbers and telling you which entry is which. And equipped with this notation, we can then pretty handily write out the key operations that are defined on these sets. So the main operations are scaling and adding, which are defined as follows. So I'll take a vector x and a real or complex number alpha, and I can define alpha x by telling you that its kth entry is the kth entry multiplied by alpha. And likewise, given x and y, I can create their sum by adding up the kth entries independently. All right, so with this nice, beautiful vector notation where I can write things in bold and explicitly refer to subscripts, I am able to very concisely and cleanly communicate how scaling and adding should work. And not just scaling and adding, we will establish other vector operations as we go forward. In particular, next week, we'll really dig into it. We'll see things called inner products and dot products and their various behaviors and properties. It's gonna be beautiful. You're gonna love it. All right, but that being said, let's go ahead and get a couple of examples of scaling and adding. So we're all good on how it works, right? Because it's all well and good to write out this very nice, precise, and concise formal notation, but you need the examples to really kind of hammer home what you're working with. All right. So here we have an element of R3, 1, -2, 3, and I am scaling it by -2. And following the rule, the kth entry of this should be the kth entry of the original multiplied by the scalar. So 1 times -2, giving me -2, -2 times -2 giving me +4, and 3 times -2 giving me -6. Right, so it's literally an entry-wise operation. If I scale by a factor, it's going to multiply each entry equally. It's not going to do anything weird, like multiply only the even ones or like multiply only the prime number ones or something goofy like that. But yeah, there it is. Cool. So there's an example of scaling. Now let's get a example of addition, and let's go complex with this one. Just so again we're just comfortable with those computations. All right. I'll take my vector 1, I, 0, and a vector -1, -1, -1, and when we add them, the rule is that the kth entry is the sum of the kth entries. So 1 plus -1 giving me a big fat 0, I plus -1 giving me a -1i, and 0 plus -1 giving me 1. Cool. All right. So that's scaling and adding in the vector world. Okay, we've already sort of seen this stuff in action because we already noted that if I've got these sort of solutions up here, you can write them in a nice, beautiful parametric form, and we can kind of pull them apart using the scaling and adding. All right, man, I killed it for time here. Oh man, jeez. Right, yeah. Well, we caught up to where the other lecture ended, so um, man, I flew for this. Jeez. All right, so let's go ahead and end a little early today. That's not too bad. All right. And in particular, let's end with kind of what our goal is going to be for next time when we start talking content again. So again, on Thursday and Friday, we will focus in on the problem list. So we'll talk about the 5 problems, and we'll also talk about how to use LaTeX to typeset things. Again, you don't need to use LaTeX for typesetting. You can use it to help you out, but not too bad. So that'll be the plan for Thursday and Friday in class. So we'll just be working on stuff in person, and homework will be due on Monday. And on Monday, our goal will be to investigate algebraic operations, algebraic properties of these operations. So we now know how to add 2 vectors. Well, we know how adding works for numbers. Adding's got 4 particular properties, right? It's associative, commutative, has an identity, and has inverses. So it'll be interesting to see if similar things hold in the vector space case. And the answer is yes, they do. Yeah, and so we'll prove some facts about how scaling and adding will work. That'll be the plan for the beginning of next week. And then we'll introduce some other vector operations and we'll start investigating those. Okay, and with that, yeah, let's go ahead. We ended right where the other lecture ended. So let's go ahead and stop the recording. and call it good for today.